Hello everyone. So today we are going to solve this equation using the Hurwitz criterion. So we've been given this equation, this characteristic equation, which is 2x exponent 4 plus 2s cubed plus x squared plus 3s plus 2 is equal to 0. So our goal here is to check whether the system is stable without solving for the roots directly. So instead, we'll construct something called a root table, which helps us to determine the stability based on the sign changes in the first column. So let's get started step by step.
To begin, we arrange the coefficients of the polynomials into the first two rows of the root table. From the equation, 2x exponent 4 plus 2x exponent 3 plus s squared plus 3s plus 2. We get first row x exponent 4, that is 2, 1, 2. Second row s exponent 3, that is 2, 3, 0. Now we will use these rows to compute the remaining rows using the determinant formula. The process continues until we reach the last row.
Hello everyone, I'm Performance and presenting the calculation for the s squared rule. For s squared, we need components b1 and b2. So b1 calculated using the formula b1 is equal to 2 times 1 minus 2 times 3 all over 2 to give us negative 2. Then b2 we calculated using the formula 2 times 2 minus 2 times 0 all over 2, which will give us b2 to be equal to 2. So then the s squared will be having a component minus 2 and 2. Thank you.
So now we compute the s exponent 1 row using the same determinant method. C1 will be equal to this, and then C1 will now be equal to 5. So the S1, S superscript 1 row becomes 5. We are almost done constructing the root table.
The last row is the S0 row, which is the coefficient of the original equation. Now S0 is equal to 2. So since S0 is equal to 2, our full root table will become S4 with 2, 1 and 2, S3 with 2, 3, 0, S2 with minus 2 and 2, S1 with 5, and S0 with 2. So now we can begin to analyze the first column.
I'm Drea Eugene and I'll be presenting on the stability check. To determine the stability of a system, we focus on the first column of the root table. The values in the first column are 2, 2, negative 2, 5, and then 2. Now, to check for stability, we observe the sign changes between consecutive values. From 2 to 2, there is no sign change since both values are positive. And then from 2 to negative 2, there is one sign change because the sign changes from positive to negative. And then from negative 2 to 5, there is one sign change as it goes from negative to positive. And then finally, from 5 to 2, there is no sign change since both values are positive. This is very important because the number of sign changes in the first column corresponds to the number of rows in the right half of the S-plane. So since we have two sign changes, it means there are two rows in the right half plane. Therefore, the system is unstable.
Hi, this is Elsie and I'll be continuing from where my colleague left off. So I'll be taking us through the interpretation part. So in the Hurwitz criterion, the number of sign changes in the first column actually tells the number of roots in the right side of the half plane. So since we had two sign changes, it means that the roots are 2 and they are positive real roots. So this makes the whole system unstable.
I'm Jeff, and I'll be talking about why the Hurwitz method matters in control systems. Polynomials in control systems can be of higher degree, let's say of degree 4 or 5, and the normal way used for solving these can be hard and time consuming as well. So the Hurwitz method was developed to solve this problem. Okay, this method can quickly determine the stability just by organizing coefficients and checking signs. That's why it is widely used in control systems. Thank you.
My name is Salome Shadafumekbo. To conclude, we formed the Routh table, computed each row step by step, checked the first system, and found 2 sign changes. Therefore, the system is unstable. Thank you for watching.